Hello and welcome again to Stephen Mendy's educational channel. In this video, we are going to first find the poles of this transfer function, and then we're going to put this transfer function into a closed loop control system with negative feedback and find the transfer function of that overall system. And then finally, we're going to examine some performance specifications, some performance metrics, and you will see how easy it is to do this. Okay? So the first thing we do is to divide throughout by 3. It's always important when doing these type of problems to make sure that we have the most significant term in the polynomial with a coefficient of 1. Okay, it works out much easier if we have the most significant term with a coefficient of 1. That would be the s squared in the denominator. So the first thing you want to do if you don't have that is to divide throughout the entire thing so that we have that. Because many of the performance specifications, the formulas, you're not expected to remember those formulas, but they work only for second order, which means we have s squared, no cubes, no fourth powers or anything. We only have a second order equation, and it must have the coefficient of the s squared term as 1. Okay, so what's the next thing that we want to do? The next thing that we want to do is use our familiar quadratic formula. There it is, minus b plus or minus the root of b squared minus 4ac all over 2a, which you should have known a long time from your early school days. We want to use that on the denominator so that we may discover whether the poles are real or imaginary. Remember that the poles of your denominator are going to determine whether you are dealing with an overdamped, a critically damped, or an underdamped system. Okay, so once we plug those numbers into the quadratic formula, there we have them all in there, and you can see how it works out. The s squared is the a, the 4 in the s is the b, and the 16 is the c. And all we need now to do is immediately we realize that the number underneath the square root sign is going to be negative, and that means it's going to be complex. We are going, or in fact, our solution is going to be a pair of complex numbers, conjugate complex numbers. So let's do it now, and we have it there. So we see we have minus 2, the real part, plus or minus 3.46j, the imaginary part. And this immediately tells us that our system is underdamped, okay? Underdamped, and oscillatory if you prefer that word. So let's go on now to do the second part of our question and put this into a system with negative feedback, a closed loop system. Now, for ease of doing this the first time around, we are going to set the feedback loop transfer function to 1. Okay, so that will make your maths very easy, because the correct formula to use for any feedback, whether positive or negative, is shown. Your element transfer function is in the numerator, and we have 1 plus your element transfer function multiplied by the feedback transfer function if using negative feedback. And if using positive feedback, then merely the plus sign changes to a minus sign in the denominator. So let's write that now. And what we have to do is just a little algebra. We have to put the whole denominator under a common denominator and then flip it and multiply. So that's done. And when we flip it and multiply, we see it cancels out and our new transfer function is shown in green. When we examine that versus our original transfer function, we see that only the rightmost number in the bottom denominator has changed. The rest is unchanged, okay? So you can go back and check that math to make sure you're happy with it. Remember that this has happened because of the way the function is and the fact that HS is only unity. Now, what we need to do now in order to say something about the performance specifications is to massage our transfer function into the following form. That number on the top is actually the gain multiplied by the square of the natural oscillation frequency. And the zeta, it's not drawn very well down there, in the middle term at the denominator, is our damping ratio, and the natural frequency figures promptly in the denominator as well. So what are we going to do now? Well, we're just going to sort of massage our above expression into that form, and we can immediately see that our damping ratio is 0.5 and our natural oscillatory frequency is 4 Hertz for this particular equation. And the K, which is the gain, is 5. So we have a gain of 5 in this particular system. Okay. So what are we going to do now? We are going to work out the settling time, which is just a standard formula. So we just have the damping ratio times the natural frequency in the denominator of that, and we work out the percent overshoot using that expression, which should be quite obvious how to do it. All you need is a good calculator, and you come out with that, and as I said, the gain is 5. Now notice that we have used the original function for our analysis of the performance of the system, not the function that results if we actually put it in a closed loop. So this is actually what would be called the open loop performance specification. This is the open loop performance specification, or the specifications for our original element. If we wanted to do some specifications for our closed loop after we put it inside the closed loop, that will be the subject of another video. Thanks so much for watching, and see you in the next video.